Good afternoon, everyone. Thank you for joining us today. I know more students will join very soon. But let's kick off the seminar program. So it's my great pleasure to introduce Dr. Bin Dong as our distinguished speaker this week. So Bin is an associate professor in the Mechanical and Aerospace Engineering Department at Syracuse University, which is not far away from us. He's also an associate director of the Syracuse Center of Excellence for Environmental and Energy Systems. His research interests include building energy efficiency, occupant behavior modeling, building to grid integration, building controls and diagnostics, and big data analytics. He has published over 100 papers and received more than $10 million funding from NSF, DOE, ARPA-E, and NYSERDA, and also industrial partners. He was a recipient of NSF Career Award in 2019, and I think before Syracuse University, he was a professor in University of Texas in the southern part of the country. So he is also serving as a research committee chair for SHRIAES Occupant Behavior Working Group, and also serving as the board of directors for the International Association of Building Physics. So he received his PhD from Carnegie Mellon University, which is the place I met him, more than 10 years ago somehow. So his presentation topic today is on occupant-centric ecosystem from smart buildings to smart cities. Please join me to welcome Professor Dong to our seminar program.
Yeah, thank you, Professor Yu. Yeah, it's my great honor to get invited to give a seminar at Cornell University System Engineering program. Yeah, so we are not far from each other. I'm from Syracuse, and I went to Cornell a few times, and a very nice campus. And I hopefully I can visit again next year sometime. Yeah, so today I will talk about my research on the occupant-centric ecosystem from smart buildings to smart cities. Next slide. Okay, so from a global perspective, we all know that probably we know that building consume a lot of energy. So this is data from 2019 that if you add up all the building energy consumptions, all the carbon emissions from buildings is more than transportation actually. So buildings is the largest energy consumed body globally. The same thing happened to the US as well. So that's why it's very important to reduce carbon emission and energy reductions in the buildings. Since now today we are talking about global net zero energy carbon emission, right? Planet. So reduce energy consumption in the buildings is the key. And also, look at government goals and policies. New York State has its 2050 goal. This is from New York State 2045 state energy goal that will have 40% reduction on the GHG and 50% on the generations, and then 33 decrease in the energy consumption in buildings from 2012 label. And the same thing happened to California. So it appears California also have aggressive goal that by 2030, by 2045, it will have 100% clean energy by 2045. So California and New York State, because there's two very aggressive state in meets government energy efficiency goals. Yeah. So when we look at, if we put a building in the urban infrastructure, you can say in the building is part of urban infrastructures. They connect with energy supply, connect with transportation, water supply, food supply, waste, and green public space. So it's not standalone. Actually, it is connected to other perspective of the urban infrastructures. And again, the cities, this is say one city and its neighborhood, and connect with other cities also connected. So, however, what is urban structure? What's the purpose of urban structure, right? So it serves a purpose to meet the needs and the demands from the people. So why we should have buildings? Because we want to have people living inside, right? Or people working in the offices. And why we should have energy supply? Because we need lighting to meet the demand of people. Why we need transportation? Is also meet the demand of people. And also the same thing happened to water, food supply, and waste and green public space. It all meets the need of the people. That's why it's occupant-centric urban infrastructure system. So I got this figure from LinkedIn, London University. They post this. They say that this is from SketchUp during lunchtime. So it's an application of controls. You can see the control. It's there are a lot of applications from the renewable energy system, from transportation, from the smart buildings, from water manufacturing, right? So I will say that they're missing. There's a missing puzzle, which is occupant behavior. So when they draw this, they never consider about, okay, when you design a complex system like controls for so many energy systems, but the occupant behavior is not considered. That is really a current state of art. Occupant behavior change everything, actually. So if we look at the urban energy infrastructure, we have smart buildings connect to the power grid. We have a power grid distribution transmission system, and we have power generations. So in this urban energy infrastructure, we know that people stay in the buildings for 87% of time. This is a survey before the pandemic. And I can guarantee you that after the pandemic, this is much more. Probably 95% time people stay in the buildings, okay? Whether it's homes or it's office buildings. And then there's a lot of smart devices, appliances, like say, Internet of Things, right? So we use a smartphone, we use a smart thermostat with a smart plug. So a lot of Internet of Things are connected together. There's like 51 billion devices by this year, 2021. And those devices actually appear very commonly in the homes. Like you have smart thermostat, the Wi-Fi control. You can even have a smart hot water temperature control. You can have temperature sensors, you have a temperature sensor at each room, occupancy sensors at each zone as well. You have, you can install PV and the battery storage system in the homes, and you probably have EV as well. And those things can be measured by the smart meter and the smart water meter as well. So you can say that, that technology is not a problem now. Technology is ready to deploy in smart homes. However, those technologies didn't consider what is occupant behavior in those homes, and what's the impact on this. This talk will talk about what is implementation that if the technology don't consider the occupant behavior, what are the impacts of occupant behavior in technologies. So this is a typical thermostat schedule for office building. And this is where the actual people's schedule look like, right? So this is a schedule, this is a schedule. They don't match. We know that. It's for sure, right? So this is what happened for the commercial building. And you can know that, okay, they don't match because there's no way to understand behavior. Okay, even you install occupancy sensor, it's a lot of noise, right? So there's no way to model that, right now in the commercial buildings. So the research question is, does human behave as we expected when we design complex engineering system? What is the impact of human behavior on system design operation? And what if we know the human behavior, how can we design advanced controls? Okay, there are 3 questions will be answered in this talk. So again, if you go back to the urban energy infrastructures, so what is, if we know the pure behavior, and then we know the technologies, what is knowledge gap between them, right? So if we, so for the using advanced control as one example, what do we want to know for the people's presence in the rooms? We want to know, is the space occupied? How many people in the room? What's the space status the next 24 hours? And what is first arrival, last departure time, in order to better control the HVAC system, right? If the space is not occupied, why should I put the temperature at 72? It should be 76. If there's only 1 people in the space, in a large auditorium, why should I put 100% outside air? It should be designed outside airflow according to just 1 people, right? And if I know what's the space 24 hours, in next 24 hours, I can design the model predictive control, right? And then if I know the first arrival, last departure time, I can also design my controls, HVAC controls, right? But this is there's 4 drivers for this behavior. So they include time, the building, the environment, and occupant. So those are all 4 drivers for this to answer these questions. And this, especially the occupant, is driven by the social, physiological, and psychological element. And especially, for example, if the occupant will never feel the same temperature need every day. Maybe this morning I get too excited because I have a talk, right? Or maybe this morning I get down because I had a car accident. So it's all driven by their behavior, driven by the social, physiological, psychological feelings, right? And maybe this morning the kids are so loud, I kind of get frustrated. Okay, it's a psychological behavior impact on my feelings. So now, because of this, the behavior is so stochastic and dynamic. It's very difficult to catch and difficult to understand. So we starting from 2007 in Pittsburgh, when I was doing my PhD, we start to put sensors into different buildings to measure what's happening in the buildings. And this is I did a test bed in the San Antonio for residential houses. We put the cameras, we put the temperature sensors and the PR sensor to understand people's behavior. This is another office building with the test bed. And this is a hotel, JW Marriott. We did a hotel study as well. We put the sensor in 5 hotel rooms to understand how people's behavior in hotels. Okay, and this is a study in 2019. This is our Center of Excellence at Syracuse. And this is the TIQ lab and the 2 side-by-side room I will present later. This is a We Are Living lab in Rochester, and this is the student dorms. So as you can see, we did a lot of actual test bed in the buildings to understand people's behavior. And also those are so different type of buildings. There's student dorms, there's hotels, rooms, there's yeah. So I just give you some examples of how people behave. So this is 16 dorms, like for student dorms. So this shows the total hourly average energy usage for total energy of September, just last month, 2021. And you can see that those 16 dorms, there's 2 rows. 341 is 8 dorms, 351 is 8 dorms. So all together 16 dorms. They all have different behaviors of how energy is used. It's so different. Okay? Everybody is different. Okay? And each dorm will stay 2 students. So basically, it's the joint behavior of these 2 students. They're all different. And this is a residential building. We did a study in San Antonio, Texas. And you can see here, there's 4 houses. They named the stick houses, ACC, container SIP houses. And this is the thermostat behavior. And some people say thermostat constant 75. Some people say thermostat is so low during the Monday to Friday, it's like 60. And some people has a regularly scheduled thermostat. So this will bring the energy consumption is so different, right? This is energy consumption for these houses. So the most advanced building envelope house, which is called it should be SIP house. SIP house is a structural insulated panel house, which has highest insulation ever. Okay, so this house should be considered the least energy. However, it consumes more energy than AC house, which is unfortunate because of the behavior of the AC. So, which means even you have highest insulation for building walls and roofs, does not guarantee you will have a least or most inefficient house. It's driven by the behavior. And now this is the dual reference model. So dual reference model means, okay, all the building design for the inefficient houses to refer to the Department of Energy reference model as a reference benchmark, which will represent the national average. In the reference model, it says the temperature should be 75 on average all the time, okay? Which is not true because there's so many dynamics, right? And this is what the DOE benchmark look like. Yeah. And we also did a study at the community level. So we collaborate with Salt River Power SRP in Arizona and April. And we study 26,000 smart meter data. And in this 26 household, there's no DRs is 5,000, and then 19,600 people has PV installed, 1,500 people have PV and battery storage installed. And this is across from 2009 to 2010, across 10 years data. And this is from 2005 to 2020, across 15 years data, to see how many PVs installed each year, how many battery installed each year. So in this study, we try to find out what is people's behavior in large scale, where the PV and battery installation reduce grid load and will reduce the stress on the grid, right? We use called a time series k-means clustering method. So this method basically we first cluster, the different patterns of usage of those houses, right? We pick 6 clusters. I can see from here among these 6 clusters, all the behavior are different. Okay, from smart meter data. These are 15-minute smart meter data. And I pick one a small set of PV installation customer I look at in detail. So the blue line is the PV, the total house load before the PV installation, and the dotted orange line is after PV installation for the house. You can clearly see the duck curve, right? This is duck curve. This is duck head, and this is in daytime generate a lot of PVs. It will reduce overall push the duck belly and this duck head. And as you see, it's clear as the duck curve, right? So, however, it still have the patterns is so different, right? This cluster 4 pattern is different from the cluster 1 pattern. There are different energy usage, right? So now we did also the look at one cluster like this cluster. Among this household with the afternoon early evening peak, like here is afternoon early evening peak. The peak period actually after PV installation is shifted to a later evening. So the blue line again is the original load, and then the orange line is after the PV installation. I can see the peak actually is shifted by 2-3 hours, and then the distribution of the peak magnitude before is before is here and after is here. So the peak magnitude is also reduced because of installation PV, okay? And then if we look at the PV plus battery storage system. So in the PV plus battery storage system, this is 12 months monthly average before and after install the battery, okay? So one thing is interesting is after install battery, the peak increased for January and February with heating. Its duck head is even higher. This is because people charge the battery at this time. Although there's the battery operates at this time, but the battery they're starting to charge the battery at this time. So actually it's increased the peak. Although the total area is reduced, but the peak increased. So this actually put a huge problem for the utility company. How much energy should be generated, right? It's very difficult to predict actually. And then we start to look at the global effect. So we did a project on the ASHRAE to build up a global occupant behavior database. So there's 32 contributions of data, involve 15 countries and 32 institutes, basically 32 universities, in contributed data. It's all over the world. And this data to measure what's the presence of people in the space, how people interact with the window opening, how people interact with thermostat, how people interact with total EV usage, how people interact with into the different buildings. Like there's a building of universities, the buildings of commercial offices, the building in the residential buildings, how people use appliances, right? So those are different behaviors. Okay, so I just gave one example. We do a cross-country comparison of first arrival, last departure time of 3 countries: Canada, Italy, and US. So they all belong to commercial office buildings. They all have very similar office arrival, not arrival, but the scheduled time for work. So you can see that they have similar peak patterns of first arrival, last departure, but they have different distributions of these 3 countries. That means people's behavior of 3 countries are different. Although they have similar patterns of first arrival, last departure as a peak time, but there's the overall pattern is different. So the answer to does human behave as we expected when we design complex engineering system? The answer is no. It's not what we expected. Everybody is different. So what are the impacts on building energy modeling simulation controls? What if we understand that people's behavior is different? How that impacts the building energy consumptions, right? So we did a study using the DOE reference model. This is a study we did last year and just published. So we have simulated three different buildings. They all belong to the residential buildings. There's 4 different foundation types. There's 4 different heating fuel types. And then we simulate also 5 different energy code versions, 40 cities, and go to Enterprise and simulate. And we have 5 different control types for the just simply control the thermostat, 5 different strategies. So we did this simulation, and we found out that, again, it's 40 US cities, 80 US different climate zones, 5 different building codes, 5 different control strategies. So we found out that most buildings can achieve more than 30% energy savings. This is assuming that, okay, I know when people will arrive home. I know when there's nobody at home. I know that when people will left home for work. So that's the assumption. So if we know that, we can have different control strategy for thermostat at homes. So this can achieve more than 30%, most buildings. And some buildings only achieve 15%, but most of them achieve more than 30%. It's a very encouraging results. And it's actually, of course, this is in the residential buildings, and it is a simulation study, right? So then we did a similar study in the commercial buildings. So this is a commercial building. So what if we know the occupancy profiles, okay, from Monday to Sunday, and the occupancy profile is so dynamic, right? What if we know that, okay? And what is how we can control HVAC in the commercial buildings, right? Okay. So this is how we control VA box according to the occupancy varieties, right? We can control airflow rate according to the number of people in the space. This is according to ASHRAE standards, basically 36, right? So we vary that in New York State, both in heating, cooling mode, and then this is results we get. So in the medium-sized office building, according to ASHRAE, using ASHRAE 90.1 2016 standards, medium-sized building can achieve energy saving between 19 to 34. Okay, so overall, right? And then in the large commercial buildings, it's less because large commercial building has more rooms, has less dynamics, so it can achieve between 0 to 90%. Okay, for large office buildings. So you can see in the commercial building, we can do that. Given the assumption, we know occupancy schedules, right? That's a simulation study. Okay, given schedules. So that's we want to evaluate impact. Now, if we know that, can we do controls? Can we design advanced controls? Again, it's also based on simulation. Okay, I will talk about field testing later, but I just talk about simulation first. Again, based on simulation. So this is study we did funded by DOE, do the Pecan Street at Texas. So we study how houses using the EV charging, right? It will come out PDF of when the house will charge the EV. So from here, we can derive, okay, what is people arrive departure time? We also look at how people use the water heater system, right, for 122 homes. And from here, we can derive when exactly people use the hot water system, okay? So then we put this into an MPC framework. We minimize the electricity price. By the way, the electricity price in Texas is so cheap. It's compared to California, New York is nothing, right? So then we minimize total electricity price. We do system dynamics in the MPC. We build the models for buildings and water heater and the EVs, and the constraints, which is the capacity of the EV charging capacity of the water heater. Okay. Now then we can say, okay, if we do this according to time of use price for the whole year simulation, we use the MPC, we can approximately can have 10 to 13% energy flexibility Okay, so we can basically how we do this. So we know when people will charge the EV, right? And we know people will leave. So we tell them, don't charge the EV now. It's peak time. Charge the EV at midnight. Okay. So when you we can guarantee when you leave, the EV will 100% charged. Okay. So this is how we do the predictive controls, based on the price, right? Time of use price. And then the same thing happened to water heater. So don't heat up the water heater now, because you know the water heater, if you don't have temperature control, is constantly maintain one temperature all the time, whether people use it or not. Okay, so we build a water tank model to tell people, okay, you should heat up a water heater at this time, based on time of use price. Don't heat up a water at other time. Okay, so that's how come out this 10 to 13% energy flexibility. Now I'm going to talk about field testing. I talk about the simulation study, right, giving very promising results. So what about field testing? Now, what does it exactly look like? So this is a SIG Center of Excellence, and we have TIQ lab on the 5th floor called Total Indoor Environment Quality Lab, TIQ lab. There's 2 rooms side by side, very unique, super unique, the only one in the world. And you have side by side rooms, and then we have installed the 3 types of people counting sensor. The first one is depth-based, which is commercially available, quite expensive, $1,000 per year, counting the people, and it's pretty accurate. And then the second one is pressure-based format. It's from some startup company. I cannot tell you, but it's from startup companies. And then the third one is RFID sensor. Actually, we got this sensor from Cornell team. So this is funded by the RFID sensor project. So there's a Cornell team. Cornell team develops the RFID sensor, detects how many people in the space. So we do side-by-side control. One room is using the baseline control. Another room is using advanced controls based on number of people. And then we monitor the energy and the fan. So this is energy monitoring. And those are the personal air conditioning stations. We call the personal air conditioning system for each workstation on the 5th floor. And this is on the fourth floor. So we made using power meter to measure consumption from this ATM. So 502 is our test room, which is office configuration. There's 10 people recruited. It's here. 503 is the baseline room. We use 10 heat bulbs to simulate occupancy heat from the load, right? That's how we do it. Each heat bulb is 100 watt. So on average, everybody emit 100 watt. Okay. So after this is what we found out. So we do almost from November 2nd to December 14th, we do consistent measurement and experiment. So there's 2 strategies. When you have people, you can control the airflow. You can also control the temperature, right? So you can say, I don't adjust airflow, I adjust temperature. Or I adjust airflow and temperature together, which airflow is from outside. So we did 2 experiments all together. So 5 days test each sensor. We can see that some sensor can reach 35% energy savings. But some sensors, like pressure mat sensors, it can only reach like 10% or 15% energy savings. It really depends on the day, it depends on the weather, depends on the accuracy of the sensor, because the sensor itself not very accurate. Sometimes the depth sensor is pretty accurate. It's reached 95% accuracy. The pressure mat reach 80% accuracy, and the RFID sensor reach 50% accuracy. So it really depends on the accuracy sensor. Tell you how many people in the space. Okay, a very interesting study. This is funded by the RFID. And the other study we did is in San Antonio Technology Center. So this one, this building has 55 offices. Each office has individual AC unit. Very interesting. Each office has individual AC unit. It's like home AC unit. It has 8,000 square footage. So we designed MPC for the each unit and implemented control thermostat. Very simple. Control thermostat, set point temperature, based on the people in the space. Okay, and we reach. Now this is a test in 2018. So we started a control in January and finished in September. And then we, this is building tier, right? So we reached like 12% energy reduction. The funny story is this. So we present a study to the building owner. Or actually, building owner present the utility bills to us. So he compares the bills, right, from 2017, 2018. And he said, there's not much savings. Where savings come from? I pay the same price. So I tell him, can you check the weather, temperature between 2017 and 18? He checks the temperature, monthly temperature. Obviously, 2018 is much hotter than 2017. So basically, you have to normalize the weather. When you do any saving, you have to normalize the weather. Okay, so that's why how we get a 12% in saving, and we got the Smart City Award, 50 award in 2019 because this field implementation. So next one, I want to talk about building to grid integration. So I know that this is a very hot topic. Actually, we started this back in 2016. So when we do smart building controls, right, we can do MPC for every buildings, right? I can do MPC for every building on the campus at Syracuse. I can persuade my facility managers to do this, okay? But when we do smart controls, what's the impact on the overall power generation, right? So Department of Energy calls this as grid interactive efficient buildings. So what we did is we built the models first. So we did power generation models, we did power generation into the mechanical and the mechanical power adjustment. And we treat the total grid load into different parts, the grid base load, frequency sensitive grid load. We don't do frequency regulations. In this time, we only do the building load control. But of course, we can do frequency regulations with the VFDs. So then we build up the grid dynamics swing equation. And the PM is power generations, and the PLK is the load demand. Okay, these are two input variables into the grid dynamics swing equations. So in the building model, we're using a 3-axis model. We build ourselves. This is a very popular model. But the difficulty with this model, you have to, in the real experiment, you have to calibrate this model, which is quite complex actually, with the large buildings. So we build this model. We're using the internal temperature as a state, and the water temperature as a state. And the input in this model is how much temperature outside, how much solar radiation in the model. What is the HVAC system, right, in the model? Okay, so this can model the. I think most people know this. This can model the indoor temperature changes. Now we put them together. So it integrates the building model and grid model together, put into giant B2G MPC. So the cost function has 4 parts. The cost due to a grid frequency deviation from 60 Hertz, the penalty of a mechanical power adjustment from set point, optimum power flow cost, and building HVAC energy cost. That is what we need to minimize object function. And the constraints are, of course, building grid dynamics, right? Grid flow, power flow balance, occupant thermal comfort in the space, and occupant presence schedules. That's our constraints, okay? So basically, we control this based on occupant schedule. Make sure on the building side, we have indoor temperature, thermal comfort met. On the grid side, make sure the frequency is not too deviate. Make sure the power, the optimum power flow cost is minimized. So this is giant B2G problem. And we did this one result is using case 57 bus system. So we have case 57 says there's 57 buses, 7 generators, 1,882 buildings. So what we found out is we have 36%. If we do coupled MPC compare with decoupled control, you can solve this control B2G problem using decoupled. Basically, what do? You simulate the building side, you pass the results into the grid side. Grid do the simulation, pass back results to grid side, building side, and building do the simulation, pass results back to grid side. You can do decoupled simulation, that's fine. But this one is we do coupled simulation. So what we found out is if we do coupled, there's 36% total operation cost reduction, 46% reduction in frequency deviation. You can see from the figure, right? So the left figure is the decoupled results. The right figure is coupled results. Upper figure is the MPC results, and down figure is the decoupled results. So there's also 16% reduction in the HVAC consumptions based on this study. It's also simulation study. And then we start to explore what happened into the large distribution network. So in the previous study, we only model 1,000 buildings, right? Or 1,000, like close to 1,000 buildings. That's very small, right? So what if we put a large scale distribution network? So we pick the largest IEEE 342 low voltage network test system. This is the largest one, low voltage test system. And then we simulate 1,500 buildings at 8 13.2 kV distribution feeders. So we simulate 15,000 buildings. So where this 15,000 buildings come from? We, using the parameters we learned from Pecon Street data, is 104 buildings. We do inverse sampling of how these buildings use the AC, how this building use the water heater, what's the schedule, how this building use the EV system. So basically we simulate 15,000 buildings with all the PV, battery, EV, hot water, HVAC can be controlled. Everything can be controlled, okay, into this low voltage network. So the result shows very interesting. So if we do this control, we can find out there's a 17% load flexibility for the AC, 21% for the EV, and then 28% for the water heater. So we basically control all the buildings, the AC, EV, and water heaters, and see how much flexible load or energy can provide to the grid. And what this means to the grid? So if we do the grid, the red line is a traditional control. It's peak at 40 megawatt-hour of the grid of this distribution network. Okay, and then if we control based occupancy, which means we provide more flexibility to the grid. So the peak reduction is about 17% for the grid, and this is only 8 feeders, right? It's 15,000 homes, but in the city there's much more homes. You can imagine how much grid can reduction on the grid peak, right? And then there's the overall energy reduction about 21% if you're using the B2G MPC framework. So it's a lot. That means if we can control every home's thermostat, every home's water heater, every home's EV charge station, we can provide a lot more flexible load to the grid. Okay, so when grid has more stress or less stress, when grid generate more energy or generate less energy than expected, we can always use building as a buffer zone to provide the energy flexibility to the grid. So this is called a grid. So now I want to spend another, I don't know how many minutes I have. Probably I spend another 10 minutes to talk about, okay.
20 You have
20 more minutes. Okay, good. So that's great. So I want to talk about, the smart buildings and smart cities, how we do study on smart cities. So when people started to energy simulations in smart cities, they use a lot of different tools. There's a tool called UMI, developed by the Christopher Renfri from MIT. There's a tool called CityBS, developed by LBNL. They're all using the NH+ engine. However, they can build a physics model, but they do not know the occupant behavior. So some tools using the stochastic agent-based models to mimic people's behavior based on time user survey. Some tools using the default ASHRAE or NH+ standards as input into this urban scale modeling tools. As I showed before, people's behavior is so dynamic, which means none of them are accurate enough to represent what people's presence, right? I use presence as example. And on the other hand, we have a lot of big data is ready. We have geotag Twitter data. We have mobile GPS data, right? We have Google Place data. We have Facebook Place data. We have Facebook check-in. By the way, Facebook just changed to name Meta. I don't know why, but the Facebook check-in data, right? And we have Google Street Views, right? Traffic data. So big data is ready at urban scale. Why don't we use part of the data, right? So the data we pick is 1.7 trillion mobile position data we used. And we start to look at the Lower Manhattan area of New York City. So this is Lower Manhattan area has 11,000 buildings. It has 3 million user IDs. That means there's 3 million users. Has 239 million rows of data records for this GPS data. Okay, so this is a user this is number of users, right? As across this 1 year. The y-axis is in million, so maximum is 6 million users. Okay, so GPS data in the Lower Manhattan area. Then we try to track one user. Very interesting, one user. So this one user has 41,000 GPS logs in Lower Manhattan, and we try to visualize it where this user has been to, where he was, or where he has been to, where his home, where his work locations or other locations. Okay, using mobility data. And then we also extract the state regions through the grid-based clustering algorithm. So based on the state points, we clustered the state points into different state regions. The state regions is a 100 meter by 100 meter block. So each block here is 100 meter by 100 meter block. So we want to understand which building he is in this block. Okay, we want to understand which building he is in. So we also look at hourly mobility patterns, and you can see on left side is users travel distance, daily mobile patterns by hour, right? How many meters he traveled. On the right side is total state points, like how many state points, like how many state points he reached, right? At different state points means different area of the whole urban area, how many places he visited. And then this is try to discover mobility patterns for different users. I just picked 6 users, and you can see the mobility pattern user are all different. It's so scattered. The data is so scattered. And this is just a visualization to show that we visualize 300,000 users with 34 million rows of data where people are. This is 1 a.m. in the morning, and this is 12 p.m. in the noon, where people are, right? So from here you can see Manhattan is here, right? And this is other areas around Manhattan in New York City. So you can see that people are 1 a.m. of course people are sleeping, right? And then at 12 p.m. a lot of people go to the Manhattan for work, and you can see the density of the people. Right? This is high density, and this is high density, and this is lower density, right? So you can actually tell at what time where people are. Okay, how many people in these commercial buildings? Okay, so then based on this idea, we did a study. We didn't use New York. We used San Antonio. We did a study to look at the impact of representative occupancy profiles for each building. How that will impact energy consumption. Okay, did a study that. So we look at the whole San Antonio downtown area. There's 980 buildings, close to 1,000 buildings. And we categorize this building into 16 different type of buildings from the DOE reference model. So which means we categorize into small office buildings, warehouses, and standalone retail box buildings, hospitals, primary schools, strip malls, large hotels, media offices. So 16 different types. Among these 998 buildings, most buildings, 191 buildings are small offices. And very interesting, there's a lot of warehouse in San Antonio. There are 156 warehouses in San Antonio, and there's small hotels, 130 hotels in San Antonio. Because San Antonio, it's a tourist city. A lot of conferences we hold in San Antonio, right? That's why there's so many hotels. Okay, so based on that, we automatically construct some models, right? So in order to do energy simulation, we have to extract the geometry of each building. Okay, that's you cannot do it manually. It's very complex. You have to do it using some tools. So we use 45 different tools, and we reclassify the LiDAR data from the LiDAR, and then we generate building footprints. We're using ArcGIS to get the height of the buildings, using AV to get the building footprint. We're using QGIS to get the address, match with the building type, and then we're using the counted text data to understand which year the building built. Okay, so this itself is a very complex process to automatically extract the building geometry into the model. So after that, So we started to look at building profile. So this is a typical architecture profile from ASHRAE 90.1. Okay, this is schedule, DOE defined. And most of building design and the simulation tool use this schedule. Okay. And this is what we found. The green line is what we found out by the measurement when we count the GPS data of all commercial buildings. It's different, right? You can say it's different. Okay, arrival time in the noon and the afternoon, they're all different. Okay, and then this is average weekly data with a 90% confidence interval. If we put a 90% confidence interval, this is profile look like. And after 90% confidence interval, you can see that some of the DOE reference model, it follow into the 90%, fall within the 90% confidence interval, which means they are good. But some of the DOE reference models, they fall beyond 90% intervals, which means they are not accurately represent what's happening in the buildings. So then we also did this look at the profile for the weekday, weekend, and set days. This is a weekend, right? They're all different. And then we come out a statistical measure called a discrepancy score to look at how similar or how different the building profile far away from the DOE reference model. So you can see that building A is a large office building, which is here. So this building, weekday, Saturday, other days are quite. This is a distinct score. The lower the score, the close the two profiles. The higher score means the far away apart from these two profiles. So from here, you can tell for large office building, the profile are pretty close to the DOE reference model. However, this is building B is a strip mall. Right? This is cannot say it's Target, but similar to Target or Walmart. So you can see that, okay, the score is very kind of scattered, which means the building profile of the strip mall is so different from what is DOE reference model is. Okay, so and then we did this all for 16 different type of buildings in the San Antonio, and we found out actually primary score, the DOE reference model assumption is the same as measured, and then we look at the number of differences. It's up to like about 24% difference, right? This is 16 different building types. So based on this difference, what is the impact on energy consumption or energy consumption without any advanced controls? Okay, so this is the impact. So we use large office as an example. Oh, sorry. We use large office example, and this is energy use difference for the large office buildings. And from here, you can see the difference is huge. So green bar is overall, which is up to like 35%, depending on which building. So the x-axis is a building number, which represent each three bar, each number represents one building. So this is about 16 large office buildings. And then it really depends on building. On average, it's about 20 to 25% difference, any difference. Okay. So now, where the difference come from, right? So the profile has differences. Where's any difference come from? So morning time has the largest any difference, up to 55%. Okay, if we plot out 6 bars, the first 3 bar is 7 a.m., 8 a.m., 9 a.m. energy difference comparison, and the yellow, the blue, and the green bar are 6 p.m., 7 p.m., 8 p.m. Difference, right? So afternoon difference has a moderate energy difference within 10% on average. So, which means if we can accurately catch or understand when people first arrive in the office, we can save up to 55% energy consumptions for the building with not advanced control, just simply schedule control, right? So just catch this number, we can know, we can save 55% energy savings. Okay. So I would like to, this is my slide, last time I talk, I like to thank my best lab members. Those are PhD master students who work in my lab. I also want to thank all the sponsors for my project. As you can see, the project are funded by DOE, and then NSA, APAE, and then NYSERDA. ASHRAE, there are a lot of different projects. Yeah. Okay, thank you. I'm going to take any questions if you have.
Thank you very much, Bing, for the wonderful presentation. This is very nice. Now I think the floor is open for questions. Any question from anyone? I see Michael raised the hand. Michael, why don't you go ahead? Oh, you are muted.
Hi, Professor Dong. Thank you for the presentation. That was really great. I have a couple of questions, so I'll make them quick. So I think around slide 31, you said there was about 30% energy savings if the occupant schedule is known. But on previous slides, I think it was for the residential example, there was a plot showing the occupancy schedule, which had very short periods of time, sometimes where the occupant would leave and then come back. Yep. And so I was wondering if the 30% is made up of counting periods like this, where it might actually be too short of a period to change the set point and save energy.
Let me share my slides. So you said slide 31?
I think, yeah, slide 31 was the 30% number, and then I think there was a slide before that was the occupancy.
Okay, so I try to answer your question. So you are saying that where the saving come from, right? Basically.
Yeah. Well.
Yeah. So
yeah,
most of the savings come from it's based on your control strategy, right? So you can control in this case, we control HVAC system every 15 minutes. So once the HVAC system understand there's no people in the space, we will put into the setback temperature. And in the simulation case, yes, I agree. In the simulation case, we're assuming the space will reach setback temperature instantaneously. But in the actual case, if you put a setback temperature into from 72 to 78, it will take some time to reach that 78 temperature.
Right.
Yeah.
Okay, thank you. And slide 52, there was a picture of, I think, an elephant. I thought that was the Docker. Is that what did you guys use?
Yeah, we use that's a Postgres SQL. That's
LPC. Oh, that's Postgres. Okay.
Yes.
And let's see. In big picture, there are newer sensors that kind of are capable of measuring biometric data on occupants. So, what do you think about the future of integrating like biometric measurement into occupant-based controls? So, the temperature of the skin, that sort of thing.
Yes. That is actually one of the project which I didn't present here. So we, in these 16 dorms, I did a further study, right? So in these 16 dorms, we actually gave students a smartwatch, and the smartwatch actually can measure their skin temperature and also the heartbeat. I think that's the future, right? So we should use as much as information possible from people. However, that also have a problem of privacy, where the occupants allow you to use those information to control the HVAC system, right? And the second question is, what's the correlation between the skin temperature, heartbeat, and with the temperature you prefer, right? So we did another study, which I didn't show here. It's a chamber test study. So we put people in the chamber, and then we read their brain signal. So we using the EEG brain device to measure the brain signal, to understand what they are thinking with the temperature and their skin temperature, heart rate. So you can see that there's not much strong correlation with the skin temperature, heartbeat, and with their preferred temperature, because the brain regulates our body temperature. Actually, it's brain, there's a regulator, regular body temperature. However, it's also people's preference and also impact by the social and the psychological effect, which is emotional, which is very difficult to predict, or unless you, like our experiment, you put a brain device to measure brain signal. Yes, you can. Without that, it's very difficult. So I would say that yes, we can use smartwatch to do skin temperature and heart rate, but it should be caution when we proceed forward. Yeah.
Okay, thank you.
Great.
Thank you.
And any other question for Dr. Dong? Actually, I have a couple, if you don't mind. This is very nice and quite close, really in the sum of what we are doing. Bing, I think first question is that how would you capture the complex geometric structure within the building? Because I do see you have this, even some sort of MPC implementation and some kind of real world testing that it's pretty much like a single room, right? But some of the building structures, indoor could be quite complicated, like some of our, old buildings on campus, let's say, right? I mean, we get multiple layers, and the way they partition the rooms is not even partition, it's just like complicated and so on. And they were kind of old as well. So for those buildings, do you have a good, I would say, simulator or physics system to capture this complexity? Because I would see like hotel room, for instance, or residential housing are somehow the easier cases, where they do have a very nice or homogeneous structure.
Yeah.
Yeah.
Actually, hotel is more complex it's very complex actually. So hotel has conference rooms, there are big hallways, there's multiple partitions, right? So our center of excellence is also very complex building. So the way we did this is we, like say, if we, first of all, you have to use expert knowledge to judge if it is a thermal zone. We call the thermal zone in this space, how many thermal zones, right? And then whether you have an actual door or wall or not, you can always put a parameter to do parameter estimation. So when you have a complex building, then your parameter are getting bigger and bigger, right? So for one room, you probably have like, 2-3 parameters, but whole building probably like 200 parameters. Okay, so there's two approaches to this. One is you put them into one problem, you identify like say 50, 100 parameters altogether. And another, which is create a high dimension problem. The other way is you do it one room by one room. And okay, you in the one room, you know that because each room you can build as the same model. The only difference is a parameter, right? So basically you identify each room has different parameters and then put them together. And then at that level, you can do you can put an additional parameter to as a coefficient to justify the parameters you already identify in the room. There's two ways to do that. Yeah.
I see.
Capture complex geometry.
Right. And how good are these simulations? Because some of these will be very computational intensive, right? If it's like CFD, and if you want to put these in the control system, it probably requires some sort of system identification or some kind of reduction. Yeah,
most of them are using system identification. You don't need to do a CFD. It's a snapshot CFD. For control problem, you don't need to do that. And also, there's a so-called faster CFD, right? It's only they only work on toy case. It's not possible in the actual buildings. Yeah, building is so complex. Yeah, so basically all you need to do is you build a complex model and using system identification to solve it. Yeah, that's one way to do it. Yeah.
I see. Thank you. The second question, if there's no one else want to chip in right now, I do see in quite a few of your models, MPC systems and discussions really focus on energy consumption, temperature, thermal comfort, right? And of course, these are relevant. Do you account for lighting in this case, and maybe also humidity, even CO2 concentration and all this stuff? Because of course, to some extent, I argue humidity is important, and also lighting, condition, if they could be controlled together, could affect the temperature and energy consumption in many ways.
Yeah, so we consider humidity in the building facade, like the envelope, heat transfer, thermodynamics, moisture transfer. But most buildings cannot control humidity. So you can only control temperature, that's it. And then in the model, yes, you can consider humidity, but in the control, you cannot control humidity. So that's why we only control the temperature. And as the lighting, yes. So lighting, we don't integrate in the model because lighting control is very straightforward. So most buildings using the so-called light sensor, a lux sensor to automatic lighting control. It's very mature. Okay, there's not much lighting control can do. The technology is very mature. And then the indoor air quality, yes. There's one project which I also didn't present here. It's an ongoing project funded by the Honeywell building automation system. So we do a couple of control of energy efficiency and the indoor air quality because of pandemic. So we do control based on infection risk of people. and try to balance the energy and the infection risk. Yeah.
That's
So
very
I didn't present here, but I just tell you this project, and there's a paper is going to publish soon. Yeah.
That's very interesting. Definitely
Yeah.
look forward to the paper. Yeah. Any last minute question? I know we are kind of running out of time. Any last question for Professor Dong? Oh, Al, you are muted.
Okay. So I'm curious with COVID, one of the things that has come out is that most of the transmission is airborne. And the way of dealing with that is to make sure this filtration, potentially HEPA filtration to control that. And I was just curious whether your center is doing anything looking into that kind of problem of optimizing filtering and changing it as need occurs. Or if there aren't many occupants, if there's no occupants in a room, you may want to make sure the temperature is correct, but you may not care about the filtration that much. So I'm just curious if you any consideration of that.
Yeah. So we did test different filtrations in our lab. We have a big chamber actually test effectiveness of air filters and air purifiers. Most air purifiers do not filter virus. They only filter formaldehyde and also other indoor air qualities. So the problem for virus is twofold. First of all, it's airborne. The second called deposition on the surface. So if the virus in the room is more than certain hours, it will attach to the particles in the room and deposit on the surface. So if the people touch the surface, it will get infected as well. So the control problem is this: how to control, make sure that there's not much of deposition on the surface, and at the same time, I can introduce fresh air into the space to flush the virus out. And also, there's some air filters like UV filters and ionizer filters. Okay, there's two different types air cleaning devices. So most people use UV. So the UV is not necessary to turn on all the time. Okay, and also ionizer will have ozone byproduct. So if you turn on ionizer, it will have ozone effect. So it will also not good because ozone will have chemical interaction with your skin care products. So in this case, the control is when to turn on the UV, when to how much outside air introduced into space, because the amount of outside air will increase the energy consumption on the heating or cooling coil, right? So there's a trade-off among there, yeah.
The reason I asked was that in many situations like aircraft, you do have to recirculate some of the air, and the HEPA filtration seems to be pretty much the solution. But of course, in other words, you have outside air and conditioning it versus filtering what's indoors, because most of the evidence now is that it's not really touching things that gets you transmission, but breathing small aerosol particles, which include virus. Yes. In the particle is virus.
Yes, yes, we did test different HEPA filters, MOS 13, MOS 14, and also other HEPA filters in our chamber test. And we literally inject virus into the chamber and look at how the effectiveness of HEPA filters, actually.
So you inject virus or you inject aerosol that includes virus?
Injects aerosol include virus. So we have a nebulizer to, kind of inject.
Okay.
Yeah.
Good. Thank you.
So it's a fake virus, but it's the same size of a virus, COVID-19. Yeah.
Thank you.
Great. I guess we are running out of time, so maybe it's a good time, to conclude now. Let's thank Professor Dong again for a wonderful presentation, and thank you for visiting us virtually.
Yeah. Thank you for the invitation. Yes.